So today's session for week 9. Okay. In week 9, now you are going to see the inner product thing. Till now, there were no inner product. I think. Let me check once. Yes, fundamental theorem versus eigenvalues, eigenvector, power. So week 9 is going to be a new concept, inner product, which is not a different, but a different kind of function. Okay. Easy. It is not so tough. Just it have a definition which you have to follow, as we usually follow the for the vector space. We didn't go through with the so deep. So very similar to that, we also follow here. Will not go to the so very deep to the inner product. Otherwise, it have a very deep concepts. It have, but will not go to the very deep. Only will understand by a simple, very simple and calculative type of definition, and you can easily uh, you can easily find the inner product between the vectors. So any feedback, anything want to say about the quiz 2? Anyone? Lengthy? No one is saying lengthy. Okay. Just a second. So question paper, as the options are there, four questions for subjective and four question for objective and three question generally if we have for subjective. So objective, if you're not even write the clear like proper uh, you know justification, still if you're writing the correct answer you'll get full mark. So in the subjective we have a square matrix. You have to find the eigenvalue, eigenvector, and it is not ask you have to find the one eigenvalues and one eigenvector. Algebraic multiplicity, geometric multiplicity is just a concept. There is no calculation. For two crowds, two matrix, justification needed for the diagonalizable matrices. This is the first subjective. The second subjective, for rank, circular matrix. Every time circular matrix, and find the eigenvalues, eigenvector of it. We have to write the circular matrix and then eigenvalue, eigenvector, just a formula. If you are writing in the formula and substituting some values in that, you will get the formula. How it could be suggested. The one, sorry, lengthy. The second lengthy, which is not too lengthy, but the third problem, which we have given matrix A and B, and you have to find the eigenvalue of A plus B using the one property. It is not asked to do the calculation A minus lambda I. That is what I said. If you use the trick, you will feel it, means it will not take time. We just write the trick. Okay, if this have this property, then the eigenvalue is going to be this, eigenvector is going to be this. And the power of that is, once you find that diagonalizable matrix, then A power 100 is just doing on the diagonals. So how it could be lengthy? If you find the trick, it would not going to be any kind of lengthy uh, question paper. And it's subjective. If you are just choosing the option, that's enough. You're not writing the justification, it doesn't matter. So third problem, I may think who don't know the trick can find the lengthy. Otherwise, the question paper is not lengthy. Okay. How Naman is saying circular matrix is finding the eigenvalue, eigenvector is too lengthy. How it could be lengthy? Do you have remember the formula of eigenvalue? Have you remember the finding the formula for the eigenvalue and for the eigenvector? Do you have to find, you have to follow A minus lambda I for that? Or if you just try the A is the circular matrix, that's all. The corresponding eigenvector is this one, corresponding eigenvector is this one, eigenvalue is this one, that's all. If you remember the formula, one, you have to just write the formula, and the next step you have to substitute the value. In the first step you have to write the formula, and the second step you have just substitute the value, that's all. How it could be lengthy? That's needed your practice. If you are now going to do with the A minus lambda I and then determinant of it, it is going to be that. Then if you have solved it like this, then how it could be? So it is become lengthy, no? So you have to use the trick. Why it is given like that? You have to understand it, right? So that's needed practice to you, not for all student even that uh, quickly do that. Just substituting in the formula. That's all. And a power and have to power for equation. So it's totally up to you who solve with the trick. Even the A plus B kind of also have the trick. You follow that, you can quickly do that. Okay, let me present my screen now. Okay, let's move to the week 9. Okay, here it is. Yeah. The new concept, inner product. I don't know how many of you have gone through with the concepts of week, lecture of week 9. So there are 9 lectures. We'll try to cover only 3. The reason is many of you, if you started watching the lecture, so at most we have finished 2 and 3. That's all. and the remaining would be covered in the next session. So orthogonal complement till orthogonal complement we'll do there. Till that we'll try to cover. So as the lecture it is, so due date is 10 for that, the next Sunday. So inner product here is inner product in R2 and C2. So if you think Professor started defining it by the definition saying to be inner product like this, where he is saying is a function from R2 to R, okay, or maybe in this if you are doing inner product within on C2, so it is going to be on C, okay, means scalar. From the vector, it is going to be on the scalar. Okay, but how it is defined? So this sign is generally used between between two vector. So see, function we use the sign generally f g h kind of, but see this f is also a kind of sign, right? So same it is a kind of that. In place of that sign, this sign, I am using this sign. That's all. And generally, if you remember, or maybe in the this case, f of x, or if it is in two variable, then if you do like this only, two variable, right? This is a two variable kind of. X is variable, y is variable. Let's say I'm writing x square plus y square. If you substitute here 1 and 2, what is going to be? This is going to be 1 square plus 2 square, which is 5. This is what generally in two variable case. Simple functions. But if you see this function is from R2 to R also. Okay. See that these two are this, it's look like same, but here this means that your vector space, okay, it is not your R2 coordinate system, okay, it is a vector space. And also this function and this function have difference. So let me show you how the difference, but yeah, I mean to say the notation. Sometimes you used to say f only, but this is also a notation of function, okay. And see how it is defined. It is defined like one vector, okay, comma another vector, okay. Let's say I'm saying 1 and 2 and 3 and 4, okay. This is the function, and how it is defined, it's surely given that. So let's say I'm saying giving x1 y1 x2 y2, okay. I'm writing like this. So this is the input in the function, as you know, x comma y. This is what generally know. So this is what it is. So similarly, this is. Now how it is defined? X1 dot x2, not even dot, x1 x2 plus y1 y2. See how it is defined? So in place of that, just need to write the value. So anyone can solve now using this definition, can answer this. What is going to be this value?
11.
11. Simply, if you see it is just a multiplication of the first coordinate with the first coordinate of the second vector, first coordinate of the first vector, sorry, second coordinate of the first vector, and second coordinate of the second vector. This is how it is multiplied, and need to add. That's all. So here it is going to be 1 plus 3, sorry, 1 into 3 plus 2 into 4, which is 3 plus 8, which is 11. See? So this is what the inner product in R2. Actually, I wrote this definition, inner product. There are actually so many inner product, okay, inner product in R2. Okay. I can define with the different definition also. Let's say I'm defining with the, so whenever it is asked, the definition would be given, okay. So let's say x1, y1 and x2, y2. Okay. So it is again, this inner product is on R2 to R, okay. This is from R2 to R. I'm defining very differently. See how it is I'm defining x1, x2 plus just y1. Okay. Now in this case, if you use this definition, what is going to be the value? Anyone can answer it?
Five.
5. This is going to be just 1 into 3. Okay, 1 into 3. And in place of y, it is just 2. So plus 2. So this is 3 plus 2, which is 5. See? So many. So this inner product is a kind of function we having. Like I am just defining the function, and according to that, I am getting the value. That's all. So simple. It is very simple. Just need to understand it. So inner product is nothing but a function, but from a vector space to a scalar. From a vector space this to a scalar. Okay. But so this is what the, so this okay, but this is not a inner product. Okay. So there is a, no, in this case here it is not a inner product, but this is a function I am saying. I am defining the function like this. Okay, somebody is want to say something. Let me check it one. Yes, Sonali.
So why you not multiply y1 into y2 in second case?
In the second case, actually, I defined. See, this is, I defined it. I defined it. I have just given the definition here. This is a different definition, and this is a different definition. So if I am saying use this definition to find the value of this, so you'll follow this definition. I said use this definition to follow the value. So I use this definition. That's all.
Okay, sir. Thank you, sir.
So I am saying the mean to say the different means this kind of notation also work like a function. As you know, function I am defining fx is equal to x square plus 2. Okay, let's say I am saying f1. Okay, I am saying now f2. f2 x is equal to x cube plus 2. Okay, so it is how so I said, okay, find the f1 value of 1. You will say 1 square plus 2, which is 2. Sorry, 3. Okay, here I said find the f2 value of 1. You will say, okay, 1 square, 1 cube plus 2, so which is again 3. But let's say here it is, I said let's set for 2 value. So it is going to be 2 cube plus 8. This is step. So see, I gave the definition. According to that, I found the value. I gave the definition here of the function, and according to that, I found the value. Similarly here, I can define for this notation, which is from R2 to R2. Okay, either I am giving this definition, according to that I have to find the value of it. I am giving this definition, but same, it is looked like same, so I can distinguish it. Let's say I am saying here it is 1, and here I am saying inner product 2. So I don't think it's, we have like, see exactly, this is f1 and this is f2. This notation here, one, it is saying f1 kind of, and this notation here a kind of f2, exactly the same kind of, nothing, no differences here, no differences. If you are getting confusion with this notation, so don't hesitate with the notation. Okay, somebody's want to say something. No, here it is a bit confusion. Somebody says the first one is also from R2 to R, and second one is also from R2 to R. Okay, this is not difference. See, I am making the same. So no one is saying the difference at R2 to R. No, it is same from, this one is also from R2 to R, because here two vectors are I am taking for the domain, and output I am getting a scalar, which is a real number. right? Here also two vectors I am taking and output getting a scalar. So I'm saying our input output are same. Input domain and output codomain is same. Only defining is different. I'm just defining f1 like this, f2 like this, or similarly inner product one is like this, inner product like this. Okay? No differences. As you used to see, this function is from R to R. This function is also from R to R. Domain codomain is not changing. Only changing the definition of the function. I'm changing the definition of the function. So this is what. Okay. So this is actually there is a bit long definition for inner product. Okay, but people used to very fear with this kind of notation. Okay, how it is. So usually when I was started studying, I used to fear with this notation how it is. Why this angle kind of two lines are there and on the some angle bracket, you can say a kind of angle bracket it is. Okay? And defined like some scalar, but it is not no need to fear it because this is just a function. Okay? So this function, okay, I'm saying this is a function. I hope all of you very less fear with this kind of notation. So actually this is a proper notation is dot and then comma and then dot. Okay, this is the proper notation for the inner product. Okay, this is the notation. A kind of mouth you are able to see it. So it's look like a, joker, a kind of joker, so as used to make it the, I mean, animated photos. So this is a proper notation of inner product. But okay, I am saying this function, okay, and I have given the definition for it. Let's say this vector and this vector. Let's say x1 y1, x2 y2, and I am defining x1 x2 plus y1 y2. I am defining like this for the time being. Let's say I'm saying this one. Okay, I'm giving another. Let's say here I'm saying that one y1. Okay, and here is x2 y2, x2 y2. Okay, and here it is I'm defining the same as above. I've defined it, x1 x2 comma. Yes, Naman.
Sir, can you go back to your previous slides where you were explaining? Sir, here you are telling that this is defined like this. You are taking x1, x2 plus y, and previously you are defining like x1, x2 plus y1, y2. So,
Hmm.
sir, if anyone has asked us to find the inner product, then what will be the answer, sir?
So that is what I'm going to tell you. See, till now I didn't said. So I said inner product word, but till now I didn't define the inner product. I'm just saying this kind of notation have this kind of definition generally have. But when we will say this function, so see this function, this is the function. This is another function. When we call this function or this function as inner product, so let's be so I am just removing whatever I said. I am some removing some word from there that many time I said inner product. Let's say this is a function and this is another function. When this function, let's say this function will satisfy some set of rule, then I will call it as the inner product. Okay, if this function will not satisfy, surely it will not actually satisfy. I will show you. Okay, then it is not going to be inner product. So you suppose you have some set of function, like let's say again you have some f1, okay, f2, some function you have. If function f follows some set of rule, I will call f as a inner product. If function f2 the same set of rule is not following that, then I will not call f2 as a inner product. So inner product is that a function satisfied some set of rule, then I will call that function as a inner product. So same case, I will tell you that how, what is the rule that. So if we check this function is actually satisfy some set of rule, I will write that set of rule. This function will not satisfy some set of rule. That's why this is not an inner product. This is just a function. This is just a function, but not an inner product. Okay, that is what I started to telling you. Now see the what are the set of rules. So I have these two functions. Okay, this angle one, let's say angle kind of angle function. Let's say I'm saying angle function, angle one function, and this is angle two function. Okay, so angle one function is okay. So angle one function and this is angle two function. Let me write some set of rules. Okay, some three rules are there. Okay, sorry, four rules are there. The first rule is that if suppose I am writing CA, I'm not writing any one or two. I'm saying for the general case. Okay, let's say I have this two. Let's say this is V1. So I'm now okay. This is let's say V1. Okay, and this is V2. Okay, if this is equal to V2 comma V1, as you know in matrix multiplication. So if I'm substituting here, just changing the position. If I'm changing the position, this should happen. It doesn't matter if I'm changing the position. So 1 minute. So still something is remain to more. The first, this is not the first rule. It is actually for the real and complex have some different set of rule. So I am writing for the real. Okay, for the timing, let's say I am doing for the real. Then for here the first rule is that if v1 comma v1, okay, I'm writing this v1 comma v1 is, this value is a scalar, no, as we found the scalar, this is a scalar value, this is always greater than 0. Okay, this angle 1 is always greater or equal to 0, and when it is 0, if it is 0, v1 comma v1 value is 0, this implies v1 is equal to 0. Okay, this is what the first rule means. If you do with the same vector, no, let's say I'm saying let's say 1 comma 1 with the same vector 1 comma 1. Okay, do the inner product. However the inner product define, if you are getting 0, that means your 1 comma 1 is going to be 0. So it doesn't, so this is true only for the 0 vector. Okay, so that is the meaning of here it is actually satisfy the 0 vector. You are getting inner product as a 0. Okay, here if it is 0, 1 minute, I'm missing something, just a second. Hmm. No, it is correct. So when it is, so it is correct. When inner product with the itself is 0, then vector itself is 0. That is the meaning of it. And inner product with the itself is always greater or equal to 0. Okay? This is the first definition. This is the first rule. The second rule is v1 plus v2 comma v3. When I am adding from the left side here, I'm adding two vectors. The third one is this one. This is always this is called triangle inequality. This is less than or equal to v1 comma v3 plus, now it's spread out, v2 comma v3. Okay, this is the second rule. Third rule is that actually for the real one, this is especially for real. If their number of terms are 2 to 2 r, okay, there is no meaning of saying. So I will separately tell for this one. Okay, for this complex have the separate, which is make difference from here only. Both have the same thing, but the make difference from complex is this one. The make difference from complex is this one. This is what the real case v2 comma v1 commutative. Okay, And one more thing is, one more definition is there. Let me check once. I think is this only three definitions? Sorry, three rules are there. Anyone have gone through with the lecture? No. So professor is started for from the complex, I think. Okay, fine, fine. Positive definiteness is called. The first one is positive linearity, symmetry conjugate. Is it started for real also? Okay, is started for real also. Definition in R2. So he didn't use the notation of this one on it. Definition for C2, definition for R2. Okay. So he actually directly joined definition. Okay, that is okay, fine. Okay, so I also jump to there. Actually, so for the time being, whatever we just said, that is totally fine. But I will also jump to the as the professor is going. Will not go to this definition. Okay, this definition is actually the inner product. Actually, definition of inner product. But whatever this definition I wrote, this is your inner product, that is called dot product, and professor started from dot product. Okay, so till here I stopped now, just now, so that is a good thing. So this is a dot product. Okay, so professor started from the dot product, so let's be on that. So dot product is, again, a dot product is, let me see how he is using the notation. Just a second. I will be also on the same notation. I don't want to make different notation. So he using dot only. So sorry, I also use the different notation. So sorry for that. So in place of this angle kind of bracket, okay, we can use the x1, y1, dot is there, and x2. Okay. So actually, this is a more general definition of inner product. I started from there. Sorry for that. So actually, this is here. This angle is actually replaced by this dot. There is a dot thing, and this is defined exactly like this. So dot product I started. So let me write here the dot product. Dot product is between the is again a function, okay, from R2 to R, and it is defined like x1, y1, x2, y2, which is nothing but exactly the same x1, x2 plus y1, y2. Okay. I just wrote the more general definition. Usually we used to write many times, means not usually. We usually write this angle, but do so forget about it. It is not there, so no need to worry. Okay, this is dot is there, and this is the definition of dot product. Okay, so this is just a, no, I'm multiplying, as in real number, as in real number, 3 into 5. Sometime you used to write dot is there, the same. This is 15. So similarly in vectors also we usually write like this, means I am multiplying a vector with this one. But when I'm multiplying with another, you don't use the word multiplying. Okay, always use the dot word. Dot product, it is a dot product, and dot product between two vector is like this. Now let's find some value. So value is there, let's say 3 5 dot 5 6 What is going to be value here? Anyone can tell? Anyone can answer this?
45, sir, 45. Sir, you are not audible, sir.
Sorry, I just got disconnected suddenly. Am I audible right now?
Yes, sir.
Okay. So he just now just one said that this is 15 plus 30, which is 45. So this is the dot product. Dot product in R2. Okay.
Sir, your screen is not visible.
Oh, sorry. Mm, okay. Okay. So this is what direct dot product means. Exactly coordinate wise, you just multiply. That's all. This is the dot product in R2. Okay. Now, see, as this one is, this is dot product. Okay. This function is from vector to vector. So same as, see, this is the vector between the dot, okay, and giving the scalar value. Okay, some scalar value here. This is a dot product in real number. Okay, so in R2. Similarly, so as this one in R2, R2 to R, okay, but in complex, it have different. Okay, it have different. What is the different in complex? Let's say I am taking inner product. I am taking two vector in complex. Let's say 1 plus I and just I. Okay, I am taking another, and here the dot product in that. Here I am writing dot, and let's say here is minus I and 2. Okay, let's say I have these two, and how it is defined there. So it's defined like this. Okay, let me write the general definition. Let's say I have this vector v1. Let me, as the professor wrote, beyond that x1 y1. Okay, so this is for real, for a scalar u1 u2. Okay, he used the notation u1 u2. So let's say this is the first vector is u1 u2. Okay, dot second vector is v1 v2. Okay, and how it is defined? So again, this dot is a kind of function. This is a function from C2 to C, that's all. So as the inner product I started, but professor don't want that angle kind of notation, he just want dot, so that's totally fine. So here the dot notation is there. So between C, this is a function. How it is defined? The defined like this. Okay. V1, sorry, U1 conjugate, U1 and U1 conjugate plus V2, sorry, U2, V2 conjugate. Is it correct? Yes, that is what it is. U dot V. So this is how it is defined. Conjugate. Okay. This is the definition. Can anyone follow this definition and find the value here? I will do that, but anyone can do quickly and find the value of it. Let's say this vector is U and this vector is V. Similarly, this vector is U, this vector is V. Can anyone find the value?
2i.
Sir,
2i.
so I'm getting I minus 1.
I minus I minus
I minus 1.
I minus 1. Okay. Let me now complete it. So this is how it is, exactly the same way we will follow. So U1 is just 1 plus I and V1 is conjugate. So conjugate, all of you know, minus I conjugate is going to be just I. So this is I here plus U2. U2 is our I and the conjugate of 2 is just going to be 2. So here it is going to be I plus I square, which is minus 1, plus here 2I. So let's say this is 2I. Oh, so this is 3I, right? So this is 3I minus 1. Yeah, I think someone got this answer also. So answer is 3I minus 1. Okay. Okay, so this is what it is. If anyone facing this, so doing this is a problem. So I am making from my side a simple simplified version of it. So the case is that let's make it this one. So U V transpose is going to be 1 minute. How it is settling up? V star is there. How it is settling? Just a second. So U1, U2. So it is not becoming that case. Let's use this definition. Otherwise, it's okay. So it is not becoming a trick. Otherwise, I will, as the professor is giving definition, it's not becoming a trick. Otherwise, I will give you a trick. Otherwise, I can give you a trick, but this is not following that definition, which is maker. Actually, there is a U transpose V kind of thing is there, but it's not following that. It's actually following U transpose V conjugate kind of thing. No matter. No matter. So let's follow this definition exactly as we find lecture. Okay. It's not becoming a trick, so we cannot do this because it is a definition. Okay, professor is giving this definition for inert product. Okay, that's why I said no. Starting, so many definitions are there. I started from so giving the so many definitions, but so many definitions, so many notations are there. But don't hesitate. Only follow the definition as defined for per lecture. Okay, like for this lecture, the inner product for complex is the definition is this one, and we'll follow this only. Okay. So whenever the inner product asks for between two vectors, we'll follow this. So this is what the inner product. Okay. Now, there are some properties. Okay, that is not needed. Okay, that is totally not needed. Okay, these definitions are actually knowing for more general inner product. Okay, here it is exactly not needed. It is the best thing is it's just to understand. I can also give this definitions. So means this properties. I will explain that. Okay, what is that property? The property is, as see in the lecture, the three properties are there, and name is that conjugate symmetry, linearity, and the positive definiteness, which I started writing there. So I started actually writing there here, but I stopped because of the notation. Okay, he's actually, so let me give the this properties. The first property is symmetry, conjugate symmetry. So what is that? If you have suppose two vector u, okay, and another vector v. So if you do dot product between these two, this is exactly dot product you want to find. This is nothing but conjugate. It will be just conjugate between the complex. So u dot v, if you do, and then sorry, v dot u, it is u dot v is v dot u, v dot u, and then conjugate. So this is called conjugate symmetry, conjugate symmetry. This is called conjugate symmetry. Are you understanding what is the meaning of it? Let me show you with the example. Okay, as the I will take here u and v the same. Okay, we have found already u and v is this one, right? 3i minus 1, u dot v we found here 3i minus 1. Let's find now v dot u and then conjugate. Okay, so actually in this definition, this u dot v and v dot u are not same. Okay, means if you multiplying left right left, as you know used to do matrix addition, or maybe matrix multiplication, as you know ab not equal to ba, the same thing is there in the here also in the dot. U dot v is not equal to v dot u. When it will be equal? When if you do v dot u and then conjugate of it. That is what it's meaning actually. So let's check it. If you we have already found u dot v. Okay, we have already found u dot v. Let's find v dot u. Let's find it. So it is going to be, can anyone tell what is going to be u dot v? So u is here, okay, and v is, sorry, v is here and u is 1 plus I, and this is I. Can anyone give that v dot u value using this definition? If you have if you are forgetting the definition.
I plus 1, sir.
Sorry, I plus
I
1.
plus 1.
I plus 1. 3i plus 1. Sorry, I just, your voice is break some places, so that's why.
I plus 1, sir.
I plus 1, just I plus 1. Okay, I plus 1. Okay. Then I'm saying, I'm surely, I'm very much sure that you are making some numeric mistake.
Sir,
Okay.
minus 3i minus 1.
Yes, this is
Yes, sir.
going
I'm
to,
also getting minus 3 minus 1.
this is what it is going to be. I also found, let's found it. So let's find it. So this is going to be, see, u is same. So here in this case, this is going to be same, and this is going to be the conjugate one. Okay, this is minus I, and this is 1 minus conjugate, because the second one always going to be conjugate. Okay, the second one is this part is always going to be conjugate. So here is this one is, you have to do conjugate. So maybe I can give you the trick. The trick is that, okay, the trick is that you can multiply, the case is that you can always, here you can, if you're doing the dot product here, let me give the trick is that you can do like this, u and dot, and we do the transpose that. Let's remove this. This is, you can use the trick, it's my side, from my side, if you means conjugate and then multiply the coordinate wise. That's all it is. So if you are facing issue, what is I mean to say, let's make it here minus I2 and the conjugate of the second one. Oh, so this is subjective, you cannot write like this. Okay, so be on the, this is subjective, if it is objective you can do. So let's be on this, otherwise be messy. So this is going to be minus I, and this is 1 minus I plus, and this is here what, 2, right? So this is 2. So 2, and here the conjugate of the second part is minus I. So now this is going to be minus I, and here is again minus and minus I square. So this is going to be minus minus plus, okay,
-1.
and minus
Minus
1. Yeah, minus 1 it is. So yeah, minus 1 it is, right? Minus minus plus and minus I square it is, and this is now become minus 2I. So this is finally, this is 3I, and this is I
Minus would
square.
come outside of the square, sir.
Sorry. Oh, sorry. So this is okay. Sorry, this is just I square. Sorry, minus minus plus and the sin square. Sorry, I square. So this is going to be minus. So I square is nothing but already -1. So finally, I mean to say I square is going to be this one. See, so many of you have found this also. So now I want to see, focus on only these two. Okay, this is here and this is here. See the differences. What is the what is this becoming? The what you found the new one, this is just conjugate, the conjugate one which you found already, right? If you do the conjugate of this is going to be minus 3I minus 1. Or maybe if you are with this one, this is nothing but -1 plus 3I, right? This is the properly we usually write. And if you have this is again the -1 plus 3I, sorry, minus 3I. Now see, exactly the conjugate, right? So that is what mean to say u dot v, okay, exactly same as v dot u, but you have to do conjugate, then it is going to be same. And this is what it is called conjugate symmetry. We can verify with the example. So this is what it is mean. This is what a professor is saying it. Okay. And the next is linearity in first argument. So I just want to tell you that this is one good thing to, you don't think always this is important. The first one is important, rest all is actually not so important, because many time people used to think u dot v exactly in the complex v dot u, but not same. It is needed to the conjugate, and then it is going to be same. In real it is exactly same. Okay, in real, if you found, let's say this is u, see this if you have the vector space R2, and let's say this v, if you do u dot v, you found 15, right? If you do v dot u, this is going to be 5 6, and this is going to be 3 5. If you do this, is again there is no conjugacy in the definition itself, so this is going to be 15 plus 30, which is again 45. So in the real dot product don't have, so in the real, in R2, this dot is actually u dot v is equal to v dot u. This is true. But in complex, this dot have the difference. U dot v equal to v dot u, but you have to do conjugate. So this is the difference between the
Actually,
complex.
sir, this complex definition also holds true in the case of real partner,
Yes,
because there is no imaginary part, so
imaginary part in the numbers.
there will be no conjugate. So it is
There is
also
no,
true in the case of the real part also.
right, exactly that is. But yeah, always you have to note it, that don't forget while doing. So actually I used to do in the whenever I used to do dot in complex, I used to forget the do the conjugate. But if you are doing an exam, don't forget. Okay, do the conjugate and then multiply, otherwise we'll be get the calculation error. Okay. Okay, so rest all these properties I am not going to tell you. The reason is it is not important. It is important when I started the, when I, whatever I have given this definition, it is actually in that relevant, it is important, but professor is actually direct jump to the particularly dot product. So that is not important. This is just knowing to be. If you know it, it is good. That these properties hold by inner product. Means inner product, conjugacy, positive definiteness. These properties hold by the inner product. Okay. Otherwise, in doing the problems in calculation, it is not important. Now I will suggest you, and even I will, from my side, if you think the homework, just do these properties, means verify these properties I just now as I verified. Okay, I verified with the examples. My suggestion is you should to also verify the remaining properties with the example. Okay, with example, and check that okay it's happening or not. If you do, you exactly under, you will now, if you just do, if you, or if you verify this property, that will become your practice system, because yourself you will try in your mind and get the answer, exactly the answer you will get. And it is a kind of verification. No, if you are if both left and right are not same, then that means you are making mistake. So again, see the definition, follow the definition, and get the answer. Okay. Now I let me move to the next concepts. Okay. uh, that is what, so this is definition, okay, of the dot product, dot in R2 and C2. These two are different now, but rest all everything I will not distinguish. Okay, and now I'm from move ahead, I will say that everything is going to be same. Okay, means the word definition, because I will use only the dot word. I will not tell you separately you are using the dot in C2 or you are using the dot product in R2. I will just say the dot product. Okay, because rest all definition are true for both. Okay, but you have to follow the definition accordingly. Which one is for C2, which one is for R2? The first is that distance. Okay, so here is distance. Now the see, in till you have, now you are doing week 9. Till now you don't know how to find, means it is not given the definition even, or ever you think that what is the distance between two vector. You have a vector, okay, and you have another vector. Ever you think what is going to be the distance between two vector? Till now there is no definition given in the lecture. And if you think that, that is a good thing, because now it is came. If you thought already, then it is good. The distance between two vectors, what is going to be that? And here is the role of the dot product. What is that? Let's say I have two vector. Let's say this is u and v. Okay, so distance between these two vectors is nothing but root of u dot v. See, now the inner product, sorry, a dot product came, u dot v. Okay, root of that. And ever you think that, vectors are kind of, this one. Ever you think that what is the angle between these two vectors? Let's say this is u and v. What is the angle between these two vectors? So now these definition started coming in your mind. Means you can see now in the lecture also, if it is coming in already in your mind, that's good thing. Okay. So the uh, this angle between these two vectors is nothing but cos theta. Cos theta is equal to, what is that? U dot v. Okay. Yeah, cos theta is there, and norm of is there. Okay, how professor is defining, let me see it, because if I will give the general definition, then again it would be a, it's better to on the, let's be on the lecture. Okay, what happened? Am I audible?
Yes, sir.
I don't know what happened with the portal. It's uh, okay. So before to start, let me give the definition because this is exactly the definition. Okay, but let me go. So let's say now, ever you think that okay. So again, my question is before to back to the angle. Ever you think that okay, this is a vector you have. What is the length of this vector? So here now these things are actually coming from the dot word. What is the length of this vector? So length is going to be the. So anyone think that using the distance word, can anyone tell what is the length of a vector? Anyone can answer this? Length of vector is using the definition of distance. Can anyone give what is the length of a vector?
Under root a square plus b square.
A
If
square b
the
square. You said the
yeah,
definition for R2 means coordinate system. I am saying for the inner product definition. This definition. Sorry, dot product definition. Just a small thing is there. Okay, I'm writing some. I'm explicitly writing here 0 0, and here is q means u1 u2.
is it v2 minus v1? You are not audible, sir. No, 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 you are not audible.
Sorry, I don't know. Actually, my side is raining. Now, is it visible? Am I audible? Also,
Yes, sir, you're audible.
sorry. Actually, my side is raining heavy, so heavy rain is there. Now I think it will. Okay, now it is fine. Let me present my screen. Okay, so am I audible?
Yes, sir.
Okay. So before to yeah, distance is fine. Uh, let's do one thing. Let's see first the norm because I use the word here norm to angle between the vector. So norm. So see this norm. I have let's say a vector 1 2. Okay. The norm is notation is like this: two between two vertical lines. Yeah, this one, and double vertical line, and the vector would be there within that. So norm of this, okay, is I will write that. I will ask you, and you can answer this. This is let's say I have a vector, let's say v, or let's say v. Okay, u. I have a vector u. So norm of this vector is I am defining like this. Okay, plus root. I will take the root, positive root. Okay, positive on root u dot u itself. Okay. Now anyone can answer this. What is going to be the norm of this vector? Anyone can answer? Norm of 1 2. I already told you this vector is from, it is automated or understood that this vector is from R2 to R2. So inner product in R2 is, again I'm writing x1 y1 x2 y2, dot is there, dot product is going to be x1 x2 plus y1 y2. So same case can we apply here? Here is the vector. Anyone can answer now quickly? Root 5, right? Because why it is, if I will do the dot product between x1 y1 y1 with the same, let's say this is your u, so this is going to be x1 square plus y1 square, right? So this is what it is. So root of x1 square means here 1 square plus 2 square, which is root of 5. This is what the norm here, okay? Norm of a vector. So in complex, it is going to be different. If I am writing 1 plus I, let's say 1 plus I and just I, so norm of this vector. So we'll follow the complex inner product rule, and according to that, we'll write the norm here. That's all it is. So this is the norm. This is called the norm of a vector. Okay. So this is one thing, norm, and there is another norm of a vector, or sometimes use the word magnitude of a vector. Okay. So I just missed that. I just wrote, yeah, that is what I started thinking. I just missed the wrong formula. It is not distance between two vector is not just, inner product u dot v. Okay, it is the norm of u minus v. Sorry, I just missed that. This is the norm. That's why this is norm of u. That I just wrote that definition. That is for angle only, and this definition is u dot v is. I just wrote no distance. That is u dot v. That is for the different inner product. I just wrote quickly. It is already in that, u dot v is already done in that case, and I just wrote for this definition. I just missed that. I thought it is going to be, but sorry for that. The distance between two vector u and v is, first you have to subtract them and then find the norm. Norm is not only norm, the root of that. Okay, root of that. And this is came the same as you are finding the distance from origin to the, that case is happening. Otherwise, let's use this definition, exactly this definition, norm of the norm of the vector u minus v. For example, let's say I have 1 2 and another vector 3 4. I want to find the distance between these two vectors. What is the distance between these two vectors? Okay. Distance. So you will do what? You will just do first find the subtraction. Let's say this is u and this is v. Okay. This one. So this is going to be 1 minus 3. The vector now you will obtain 1 minus 3 and 2 minus 4. This is how it is. This is minus 2 and this is minus 2 again. And now norm of this one is, now you can use the formula directly, x square y square kind of thing. This is minus 2 square plus minus 2 square, which is 4 plus 4, 8, and which is 2 root 4 into 2 root 2. Okay, so this is the distance. Now angle formula is this one, you can directly use. This is what the, now nothing is not nothing is, this is just a formula. Cos theta is equal to, this is for real value of, this is for complex case. Okay, this is for complex, so I just wrote for the real one. So this formula is for real vectors. For the complex one, or the complex vector is this formula will use generally. RE u dot v, and then norm of divided by the norm. Cos theta is equal to. Okay. So for the real one, it is just become u dot v. Trigonometry is already done in maths one mostly, so we want to do it. So in the real one, this is just u dot v and divided by the norm. Okay. So this is going to be, I will at most, so that's why I fix the last lecture is I am going to do. A very small thing is there even in that. The orthogonal complement. It is just the inner product definition is there. Okay. So angle is you will just follow and means here you will just follow the definition here, u dot v, and then cos theta value. You know the trigonometry means you are just to substitute the values and find the angle between the vectors. Yeah, this third lecture is now important and a very different uh, notion is there, which is called complement. Okay. So sometimes called orthogonal also. Okay. Where it is this one. Orthogonal complement. Okay. Dual it is called, or dual it is called orthogonal complement. So what is that means? The thing is, let's say I have a vector, okay, some set of vector. Let's say I have this vector 1 2. Okay, let's say I have only not set of vector. Let's say I have this vector 1 2. I want to find a vector. When I will do the dot product with this, it will give 0. It will give 0. What is going to be in the at the blank space? What is going to be that? Anyone can answer it? This is just solving the linear equation, system of linear equation it is going to be. So as you know, if we just do the dot product, no, here it is, I can use, let's say this variable is x1, let's say this is v. I'm just multiplying with these two. So this is going to be x plus 2y
X plus 2y is equals 0.
equal to 0. And now this is, a kind of system of linear, one equation you got. So for this vector, for vector this one, you will not only one vector. There are infinitely many vector. As you know, this system has infinite. This is with the two variable and one equation is there. This system has infinitely many solution. You can write like x is equal to minus 2y. Now you can give y value as 1. Then you can, sorry, y value is 1. You can get x value is minus 2. So this is one value. Now you can change the value. You can replace, so you can see y is equal to some any scalar. Then x is equal to minus 2c. So finally c and 2c kind of minus 2c will get, which is a kind of c time minus 2 and 1. Right? So you will change c values any 0, 1, 2, 3 kind of anything, and you will get so many vector. So for this vector, let's say this is I'm saying u. For u vector, which is 1, 2, the orthogonal complement of this one is not only single vector, which is not only minus 2 and 1. So many vectors are there. Now if you check, you want to verify it. Let's say I'm checking with this vector minus 2 and 1. This is 1 and 2 and dot with the minus 2 and 1. See what you will get. Minus 2, 1 time minus 2 plus 2 time 1, which is 0. See, this is what it's becoming. So for this vector, you will not orthogonal, means this is called orthogonal complement. The representation is u and above a kind of ulta t, okay, vertical t is there. So this vector is there. So you complement. So this orthogonal complement is not only single vector, it is actually so many vectors. Not only this is called space, subspace, sorry, this is a subspace also. Orthogonal complement is not only the space, this is actually not only a set, it is a subspace. Okay. But for the timing, I think professor said also that it is not going to be one vector, it is going to be a set. So, but the set is, you can, if you want to write u orthogonal complement, it is going, you can write like this: c time the vector minus 2 1, okay, where c belongs to scalar. This set is called orthogonal complement. Okay, you can choose one vector and you can multiply, that is, you can check that this is a orthogonal complement, means orthogonal to 1 and 2. And the vector, okay, so I directly use because of the quick thing. So let's say I have a vector a and b. Let's say I want to find a vector x and y. If you multiply, you will get 0. So this vector is called orthogonal vector. Okay, orthogonal vector to this, where orthogonal vector of this one. That is what the meaning of it. And this set is called orthogonal complement. Okay, this set where your collection of all vector which is orthogonal to u, it is, that is orthogonal complement. The orthogonal definition is, you have this given vector 1 2, you found a vector which is minus 2 and 1. When you are doing the dot product, it's become 0. Then you can either, you can say these two vectors are orthogonal to each other. Okay, this is what the third lecture. And this lecture is not too big. Check it once. Only just this definition is there: orthogonal complement or orthogonal thing. 9-minute lecture is there, a small lecture. It's just defining that what is orthogonal and what is the meaning of orthogonal complement. See, this is orthogonal complement is defined like a set, and orthogonal means a vector which is orthogonal to other. This is a subspace. Okay, so this is a subspace. And now he started telling you the with the example. Okay, this is what it is. Now the remaining thing is, we'll see in the next session. The one thing is that many of you didn't go through the, so now at least you start with this definition, we'll get idea, okay, these all the definitions are there. And like, at least if you understand from the scratch that what is a dot product, and dot product in C2, dot product in R2, then norm, distances, angles, and you can see it, you can do practice yourself. And there is a orthogonal complement is there, and rest all, if you see the topics is, will be around it, will be around it. Adjoint is a kind of orthogonal, you will see there. Range null is already, you have seen it. Okay, so again, now the same things start coming: eigenvalues, eigenvector of some special kind of adjoints, means which is called Hermitian. So concepts of after this, these three are actually a bit longer. Now onward, the concept are small. Only small topics are there, and we'll quickly understand. This inner product is, I started from scratch to understand it. Distances, orthogonal thing. These are the important. Yes, Sonali.
Could you please explain that the criteria which is followed by to uh, follow the dot product of the which you had
Uh,
written there?
yeah, I wrote the criteria, but I thought maybe that is what I thought. Maybe professor started from general definition, so don't use it. Okay, that criteria, I know that is not needed for this lecture or this course. That criteria is not needed. Professor taught
Okay, sir.
that by a properties. He was that telling, that is what is telling, the properties of the dot product. I thought maybe
Okay, sir.
professor started from the definition of dot product, so that's why I started, but that doesn't need it here. Okay.
Okay, sir. Thank you, sir.
Yes, that is not needed. So these things are there. Just spend time. You can. So easily this. So now inner product is kind of do more, not more calculative, means one by one kind of thing, numerical, like as you used to do the multiplication. So actually dot product is a function from R2 to R. Okay. And the ahead lectures are small, so not tough. You have seen already eigenvalues, eigenvectors. Okay. Adjoint is just transpose, conjugate transpose. So these ahead topics are very simple. Okay, very easy now. So now all of you go through with the lectures. It will be, you will find easy. Okay. Thanks everyone. Thanks for joining. We'll meet on
Thank you,
next.
sir.
Okay.